from Coulomb's law. Coulomb's law says that electric field is a vector, and electric field is equals to 1 by 4 pi epsilon 0 into q by r square and r cap. What does it mean? Say there is a charge q and there is a point p, and we call it the charge the source, and this p point is some field point, and where we have to find the electric field. So the distance between the source and the field point is r, and now the equation explains itself, and the direction is according to r cap. Okay, so this is the electric field, mathematical form of electric field. But how it looks like, that is the question. How it looks like. So visualization was always good for everything. Every understanding, visualization is needed. So who was first thought about this? His name is Michael Faraday. So Michael Faraday was the first who tried to visualize the thing that is vector E. That means electric field. So he used some lines. Why he used some lines? Because electric field itself is a vector. Okay, and we represent a vector by a line. Is it okay? So Michael Faraday used some lines, and these lines called electric lines of force, and they have some properties, and we will discuss the properties. These properties are very important to construct electric lines of force. Okay, and number A is that field line starts from this very important idea, that starts from positive charge. Okay, this is just a convention. The world maintain this convention only, that you can say that, okay, why I cannot say that it is negative? You can take it, but the world sees that, world says, everyone says, every physicist, just it's a convention that is a positive charge from where the field line starts or emerges and terminates. And this is also important, it terminates to negative charge. So how it looks like? Okay, let's see how it looks like. So say there is a positive charge and there is a negative charge. So the field lines will emerges from positive charge to the negative charge. Okay, so you cannot draw like this one. No, this is not true. So positive to negative, and you have seen in many books that there are some curves and many things, and I will explain it, why they are curves and why they are straight line, etc. So positive charges emits some field lines. This is the property of the field lines. Next property is also very important. Every property is very important. What next property says? That field lines behaves like a tensed wire, like a tensed wire. You don't remember, tensed means tensed wire. That means it looks like that there is a tensed wire. This is some field lines concept, that it is a tensed wire, that you have fixed this point and this point, and you build up some tension. Then we can say that, okay, it looks like a field lines. But this wiggly, no, these are not the field lines, because they are not in tension. Okay, so field lines must be in tension and behaves like a tensed wire. It is a mechanical, we can write down here, it is a mechanical analog. Okay, it is a mechanical analog that the field lines behaves like a tensed wire. So there is next property that we are going to write down, point C, that every two lines they repels each other. Two lines repels each other. So this is repels each other, and this idea, this property explains the repulsion of some electric charges. Say there is two charge, like positive or negative. Okay, positive to negative, and we found that the lines are some straight and stretched wire, like a stretched wire. Now, say there is two lines and do two parallel lines, say A and B. The line A will exert some force on B and it repulses. That means force is outward. And also B exerts some force or repulsion on A and it is outward. And according to this thing, the result will be something like this one. Okay, something like this one. These lines will bend, and that's why you see that if there is some charges plus and minus, there are some bending. Okay, not all, but some bending is there, because the nearest lines tries to repel the other. And if you see that this line is straight, because this line repels to this word and this line repels to this word, so there is no net repulsion. Okay, so you are going to understand that how repulsion works and the field lines. There are more things. Let's see the point D. The fourth point is that about the direction of the field lines. So the field directions at any point, so we have to find the field direction at any point, field direction at any point. If you want to find that, because the electric field is a vector, so you have to find the direction at any point is the tangent. Very important idea, the tangent on the line, on the field line, I mean on the line at that point. So we will draw it and we will try to figure out it. There is a line, this is a field line, and you have to find the point P, at point P, and at point L. So what we'll do, you will just put some tangent here. So this is the direction of electric field at that point P. And what about this? Draw some tangent and you are getting some EL. That is very interesting that it is changing here. Okay, so these are the direction of the electric field lines, and I will explain it more, because we need to understand how it construct. That means field line construction. So if we put some lines here, and we know now why these are bended line. Okay, why these are like this or like this? Because of repulsion. Okay, so these are the field lines. So if you have to find the electric field direction, then let's say in this point, and you will find that this one. But you can say that, okay, why we can draw in that direction? Why we can draw in that direction? Because field line emerges from here. That means field direction is the like this. So you have to draw this direction. Okay. Now, if we want to draw, what about this point? So you have to draw like this. So electric field lines are like this. Electric field lines describe the direction of electric field at like this. Okay, by the tangent. Field lines describes also the intensity of electric field, and it is electric field intensity. So we have found the direction, and now we are going to find the electric intensity. I mean field intensity, obviously. Electric field intensity is proportion to the number of lines, passing through the unit area. Okay, the number of lines passing through unit area. Okay, and it is not the same thing. The last thing we have to say it more, because there are something else. Because when we are talking about the area, then the area has a vector. It is a vector. As area is a vector thing, so we need some direction to the vector. So we have to write that the number of lines passing through unit area normal to the field direction. normal to the field direction, normal to the field direction, and later we will know that this will be called flux. This will be called actually flux. Okay, flux. uh, so what it looks like, let's see, let's visualize it. Okay, say there is a some area, I'm getting some perpendicular area obviously. So now there is passing some field lines, okay. So unit area, this is a unit area, let's say this is an unit area, and it has some direction, say this one. Okay, so number of lines passing here is 1 2 3, so electric field intensity will be 3. And if we have 5 lines passing, so we can say that it is electric field intensity is 5. Or if sometimes you will find that this direction and electric field is passing through this one like this, so now the perpendicular direction is here, that means area direction is something changed, so you have to calculate it by dot product. We'll do dot product and we'll discuss it later how it works. Okay, but now these are the idea of electric lines of force, and we'll discuss some mathematics later. So are we done? No, we are not done yet. We have something important still. Look, electric field lines is a 3D representation. Okay, look like this one. So electric field lines are 3D mapping. We are saying that this is a 3D mapping. So if we put some charges here, there is no direction yet. Say this is a positive charge and this is a negative charge. So the field lines will emerges from here to there, from here to there. Okay, if you say this one, this line, then the direction will be there and the direction will be there, and so on. And it is a 3D idea, but in book you see something different, and this is what we see, that is 2D projection, 2D projection of the 3D. 2D projection, how it looks like? It looks like this. If this is a positive charge, just compare, and this is a negative charge. So the idea is that the positive charge, the field line emerges from positive and it ends to the negative. It is just a cross-sectional area, you can say, also a 2D projection, you can say anything. Okay, so this is our idea of electric lines of force. And last thing that electric field has some unit also. Unit is an important idea, that unit is volt per meter square or Newton per coulomb. So these are the unit of the electric lines of force.